Hello friends, I am Muhammad Azhar Iqbal Nawarkhan, Assistant Professor of Physics, Government First Grade College, Mundargi. Today we are going to discuss the Thevenin's theorem. In the previous class we have studied the basic terms and definitions of electronics and Kirchhoff's current law, Kirchhoff's voltage law and sign conventions, voltage source, current source. Now, today we will discuss the Thevenin's theorem. The statement of the Thevenin's theorem is any two-terminal linear network containing sources of EMFs and impedances or resistances can be replaced by a single voltage source in series with a single impedance or resistance. That is, if n number of resistance and n number of impedances are there in the circuit, that can be replaced by a single voltage source in series with the single impedance. The EMF of the voltage source is equal to the potential difference between the terminals of the network when no external circuit is connected to them. The series impedance or resistance is equal to the impedance between the terminals when all the internal sources of EMFs are replaced by their internal resistances. The equivalent voltage source is called Thevenin's voltage and is denoted by VTH, and equivalent impedance is called Thevenin's impedance or resistance and it is denoted by RTH. Now the simple circuit is here. A battery is connected to the resistance R1 and a resistance R2 and a load resistance RL. The equivalent circuit of this circuit is like this. The EMF is replaced with the constant voltage source VTH and the two resistance are replaced with a single equivalent resistance RTH is connected with the battery in series and the two terminals A and B and a load resistance RL. According to Thevenin's theorem, the load current IL through the load resistance RL connected in the above network equivalent circuit, IL is equal to VTH divided by RTH plus RL, where VTH is the open circuit voltage across A and B when RL is removed. RTH, effective resistance or impedance between the terminals when all the sources of EMFs are replaced by their internal resistances. Now we will see the proof. The simple circuit diagram. Here we have to consider first mesh is the E, R1, R2, E, and the second mesh is the A, RL, B, R2, A. Now apply the Kirchhoff's law to the mesh E, R1, R2, E. Here minus of I1 into bracket small r plus R1 minus of I1 minus IL into R2 plus E is equal to 0. The first one is taken as negative because we are moving in the direction of the current, and small r is the internal resistance of the battery and R1 is the resistance. Both are connected in series. And minus of I1 minus of IL is also taken as negative because we are moving in the direction of the current. Now this equation can also be written as I1 into bracket R plus R1 plus of minus I1 minus IL R2 minus of E is equal to 0. That is I1 into, if we solve this equation, we will get I1 into bracket small r plus R1 plus R2 minus of IL R2 is equal to E. Call this as equation number 1. Applying Kirchhoff's law to the mesh A, RL, B, R2, A. Minus of IL, RL plus of I1 minus IL bracket complete into R2 is equal to 0. IL, RL minus of I1 minus IL into R2 is equal to 0, or IL, RL minus of I1 R2 plus of IL R2 is equal to 0, or I1 R2 is equal to IL into bracket R2 plus RL, or I1 is equal to IL into bracket R2 plus RL divided by R2. Call this as equation number 2. From equations 1 and 2, IL into bracket R2 plus RL bracket complete divided by R2 into small r plus R1 plus R2 minus of IL R2 is equal to E, or IL into bracket R2 plus RL into small r plus R1 plus R2 bracket complete minus of R2 square divided by R2 is equal to E, or IL into bracket R into bracket R2 plus RL bracket complete plus of R1 into bracket R2 plus RL bracket complete plus R2 bracket of R2 plus RL bracket complete minus of R2 square is equal to ER2, or IL into bracket R small r into R2 plus small r into RL plus R1 R2 plus R1 RL plus R2 square plus of R2 RL minus of R2 square is equal to ER2. Plus R2 and minus R2 get cancels. IL into bracket R2 into bracket R plus small r plus R1 bracket complete plus of RL into bracket small r plus R1 plus R2 is equal to ER2. IL is equal to ER2 divided by R2 into bracket small r plus R1 plus of RL into bracket R plus R1 plus R2. Dividing numerator and denominator by small r plus R1 plus R2, we get IL is equal to ER2 divided by R plus R1 plus R2 whole divided by R2 into bracket small r plus R1 divided by small r plus R1 plus R2 plus of RL. Call this as equation number 3. Remove RL from the network. The circuit will look like this. From the figure, it is clear that open circuit voltage across AB is equal to VOC or VTH. That is equal to voltage across R2. That is equal to I1 minus of IL into R2. But I1 minus IL is equal to ER2 divided by R plus R1 plus R2. Therefore, VTH or VOC is equal to ER2 divided by R plus R1 plus R2. Call this as equation number 4. Now, remove the EMF or replace the EMF with its internal resistance small r. The Thevenin's resistance between A and B is given by R and R1 are in series, R plus R1, R2 are in parallel, R plus R1, R2 are in parallel. Then 1 by RTH is equal to 1 by R plus R1 plus of 1 by R2. 1 by RTH is equal to R plus R1 plus R2 divided by R2 into bracket small r plus R1 bracket complete. Therefore, RTH is equal to R2 into bracket small r plus R1 divided by R plus small r plus R1 plus R2. Call this as equation number 5. Comparing equations 3, 4 and 5, we get IL is equal to VTH divided by RTH plus RL. Now we have to follow some procedure steps in finding the Thevenin's equivalent circuit. First, you have to remove the load resistance from the circuit. Find the second one, find the open circuit voltage across the terminal. This is called as Thevenin's voltage, VTH or VOC. Third point, determine the equivalent resistance of the network as looked from the terminals when EMF are replaced by their internal resistance. This is known as Thevenin's resistance and it is denoted by RTH or RI. Fourth one, replace the entire network by a single Thevenin's voltage source VTH with a resistance or impedance RTH connected in series with VTH. Connect RL across the terminals. Calculate the load current IL by the equation IL is equal to VTH divided by RTH plus RL. The important equation terms in the Thevenin's theorem session is that the first one is the Thevenin's theorem, proof of Thevenin's statement, and measuring Thevenin's voltage VTH or VOC by VTH or VOC is equal to ER2 divided by R plus R1 plus R2. Measuring Thevenin's resistance RTH is equal to R2 into bracket R plus R1 divided by R plus R1 plus R2. Replace the entire network by a single voltage source in series with a single resistance. Calculate the load current IL is equal to VTH divided by RTH plus RL. Now, depending on the above section, we have some questions. Question number 1. The Thevenin's voltage is the options are open circuit voltage, short circuit voltage, open and short circuit voltage, D, neither open nor short circuit voltage. The correct answer is open circuit voltage. Question number 2. Thevenin's resistance RTH is found. The options are A, by removing the voltage source along with their internal resistances. B, by short circuiting the given two terminals. C, between any two open terminals. D, between same open terminal as for VTH. The correct answer is between same open terminal as for VTH. Question number 3. Thevenin's theorem is true for. The options are A, linear network, B, non-linear network, C, both linear and non-linear network, D, neither linear network nor non-linear network. The correct answer is linear network. Question number 4. Thevenin's theorem cannot be applied to. The options are A, non-linear circuit, B, active circuit, C, linear circuit, D, passive circuit. The correct answer is non-linear circuit. Question number 5. Which is the correct sequential order of steps to be undertaken while applying Thevenin's theorem? A, calculation of Thevenin's equivalent voltage. B, removal of branch impedance through which required current is to be estimated. C, estimation of equivalent impedance between the two terminals of the branch. D, estimate the branch current by schematic representation of Thevenin's equivalent circuit. The options are A, first option A, C, B, T, B, B, A, C, D. The third option is D, A, C, B. The fourth option is B, C, D, A. The correct The option is B.A.C.D. First, you have to remove the branch impedance through which the required current is to be measured, calculation of Thevenin's equivalent voltage, estimate the equivalent impedance between the two terminals of the branch, and then estimation of branch current by schematic representation of Thevenin's equivalent circuit. Question number 5. Can we use Thevenin's theorem on a circuit containing BJT? The options are no. First one. Second one, yes. Third one depends on BJT. Fourth one, insufficient data provided. The correct option is no. Question number 7. Thevenin's theorem applies to. The options are A. One-port network, B. Two-port network, C. Three-port network, D. Four-port network. The correct option is two-port network. Question number 8. In Thevenin's theorem, we measure. The options are voltage, B. Current, C. Both A and B, D. Neither A nor B. The correct answer is voltage. Question number 9. In Thevenin's theorem, we calculate. The options are A. Voltage, B. Current, C. Both A and B, D. Neither A nor B. The correct option is current. Question number 10. In Thevenin's theorem, load current is calculated using the formulae. The options are A. IL is equal to VTH divided by RTH plus RL. B. IL is equal to RTH plus RL divided by VTH. C. Either A or B. D. Neither A nor B. The correct option is IL is equal to VTH divided by RTH plus RL. We have referred the books Fundamental of Physics by Halliday, Resnick, Walker, 2002 edition. Principles of Electronics by V.K. Mehta, Rohit. Thank you.